At nearly 11 kilometers below the surface of the Pacific Ocean, there is a place where the rules we take for granted begin to quietly fall apart. It is not distant in the way space is distant. It does not sit beyond our planet, hidden behind vacuum and radiation. It exists here, beneath us, underwater, so ordinary at the surface that ships pass over it every day without noticing what lies below. And yet, the Mariana Trench remains one of the most extreme environments known anywhere on Earth. Not because it is far away, but because it is so difficult to truly experience. If you were to take Mount Everest, the tallest point on land, and lower it into this trench, its summit would still be submerged beneath more than a mile of water. That comparison is often repeated, but it only begins to hint at what this place represents. Yeah, height is something we can visualize. We can imagine standing at the base of a mountain looking up. Depth is different. There is no vantage point from which to look down 11 kilometers of water. There is no perspective that makes it feel real. The trench is not simply deeper than anything else. It is beyond the scale our senses evolved to understand. As you descend through the ocean, the change is gradual at first. Sunlight fades into a dim blue, then into a darker shade until it disappears entirely. Temperature drops steadily. The water grows denser, heavier. Pressure builds with quiet consistency, adding another atmosphere of force roughly every 10 meters. At a depth of 100 meters, you're already under 10 times the pressure experienced at the surface. At 1,000 meters, 100 times. And this accumulation does not stop. It continues, uninterrupted, all the way down. By the time you reach the bottom of the Mariana Trench, the pressure is more than 1,000 times greater than what we experience in everyday life. It is not a force you would feel as pain or impact. It is constant, uniform, pressing in from every direction at once. Steel bends under it. Materials behave differently. Structures that feel solid at the surface become fragile when exposed to that kind of compression. It is an environment that does not tolerate weakness or error. It does not need to be violent. The force itself is enough. And yet, pressure is only one part of what makes this place so extreme. Long before you reach the bottom, long before the pressure becomes truly difficult to comprehend, something else disappears. Light. Sunlight does not penetrate very far into the ocean. Even under the clearest conditions, it fades completely within the first 1,000 meters. Below that, there is no day or night, no horizon, no shadow. Darkness is not something that arrives suddenly. It thins gradually until it is absolute. Without sunlight, the foundation of most life on Earth is removed. Plants cannot grow. Photosynthesis cannot occur. The entire energy system that supports ecosystems on land and in shallow water no longer applies. For a long time, this led to a simple assumption that life at these depths should be rare at best, perhaps absent entirely. It seemed reasonable. Without light, without warmth, without a reliable source of energy, there should be nothing to sustain complex organisms. The trench reinforces that expectation in every other way. Temperatures hover just above freezing. Movement is slow. The environment is stable in a way that feels almost static. There are no storms, no waves, no visible weather. It is easy to imagine this place as empty, not because we have seen that it is empty, but because everything about it suggests that it should be. For much of human history, this assumption went unchallenged. The deep ocean was simply too difficult to reach, too hostile to explore. Early scientists believed that life might not exist beyond a certain depth, that pressure alone would make survival impossible. It was not an unreasonable conclusion. At the time, there was no evidence to suggest otherwise. The deeper the measurements went, the more extreme the conditions became, and the more certain it seemed that there must be a limit somewhere. But the trench has a way of quietly contradicting certainty. It does not do so dramatically. There are no obvious signs from the surface, no disturbances in the water above that hint at what lies below. Its resistance is subtle. It simply refuses to match our expectations. Because despite everything that should prevent it, despite the darkness, the cold, the immense pressure, and the absence of sunlight, life exists there. Not just in the sense of microscopic organisms clinging to survival, but in forms that move, feed, interact, and persist. Creatures that have never seen light, ecosystems that function without the sun, biological systems that operate under conditions that would disrupt, distort, or destroy most life we are familiar with. The deeper scientists looked, the more this contradiction became impossible to ignore. This is what makes the Mariana Trench so compelling. It is not just the deepest place on Earth, it is a place where the assumptions we build our understanding of life around begin to fail. A place where the boundaries we thought were fixed turn out to be flexible, where the absence of what we consider essential does not lead to emptiness, but to something else entirely. And the deeper we go, the more that contradiction sharpens. Because the trench is not a single environment, it is a progression, a slow removal of conditions one by one until what remains should no longer support anything at all, and yet it does. And that contradiction becomes easier to understand only if you follow the descent all the way down, not as a single drop into darkness, but as a gradual stripping away of everything life is supposed to depend on. Because the ocean does not become extreme all at once. It changes in layers, each one removing something familiar, each one quietly rewriting what survival looks like. Near the surface, the world still feels recognizable. Sunlight penetrates the upper water, warming it, illuminating drifting particles and vast schools of fish. Plants grow here, microscopic but abundant, forming the base of nearly every ocean food chain. Movement is constant, energy is plentiful, and life behaves in ways that feel almost terrestrial, only softened by water. But even within the first few hundred meters, something begins to shift. But light does not disappear suddenly. It fades, losing intensity with depth, thinning into a dim blue glow that reaches downward but never quite arrives. Colours vanish first. Reds disappear almost immediately, followed by oranges and yellows, until everything is reduced to shades of blue and grey. Objects do not look different because they have changed, but because the light that reveals them has been filtered away. This is the beginning of a transition that continues for kilometres. As the descent deepens, the sun loses its influence entirely. By the time you reach what is known as the twilight zone, the light that remains is no longer sufficient to support plant life. Photosynthesis stops here. The primary energy source for most ecosystems on Earth is effectively cut off. Above, life is driven by sunlight. Below, that connection is severed. This boundary is not marked by a line or a sudden drop. It is a threshold that, once crossed, cannot be reversed, and yet life continues below it. At first, it seems like an extension of what exists above. Fish still move through the water, though more slowly. Their bodies become darker, often black or deep red, colours that make them nearly invisible in the dim light. Eyes grow larger, adapted to capture what little illumination remains. Everything feels like an adjustment, a slight modification of familiar forms. But this adaptation has limits. Continue downward, and the twilight gives way to something else entirely. The midnight zone begins where light disappears completely. There is no residual glow, no sense of direction, no difference between up and down except what instruments can tell you. Darkness here is not the absence of light as we experience it at night, where distant stars or scattered reflections still exist. It is absolute, a condition rather than a lack. Vision, as we understand it, becomes almost useless. And with the loss of light comes the loss of something deeper than visibility. It removes the need for colour, for camouflage based on sight, for the entire visual language that defines most ecosystems. Movement changes. Creatures drift more than they swim, conserving energy. Many produce their own light, not to illuminate the world, but to communicate, to attract, to deceive. The deeper you go, the more it becomes clear that life is no longer shaped by the sun. It is shaped by absence. Temperature continues to fall, stabilizing near freezing. The water becomes heavier, more resistant to movement, and pressure builds steadily, never pausing, never easing. By now it has reached levels that would already be lethal to most surface organisms. But even this is not the final transformation. There is another transition waiting below. Beyond the midnight zone lies the abyss, a vast expanse of seafloor stretching across the planet, deeper than most of the ocean, but still not the deepest. It is here that the scale of the ocean becomes difficult to grasp. The seafloor is not jagged or dramatic in most places. It is flat, covered in fine sediment that settles slowly from above. This is where the ocean begins to feel less like a place and more like a system operating on timescales, too slow to observe directly. Life exists here as well, but it is sparse, patient, adapted to scarcity. Food arrives slowly, in the form of tiny particles drifting down from the surface, a constant but minimal rain that sustains everything below. It is enough to support life, but only just. And then, beneath even this vast and quiet world, the ocean deepens again. The seafloor does not remain level. It breaks, folds, and drops into trenches that cut into the planet's crust. The Mariana Trench is one of these places, but it is the most extreme of them all. This is where the descent reaches its final stage, where the gradual loss of conditions becomes complete. By the time you enter this region, known as the Haddle Zone, everything that once defined the surface world has been removed. There is no light. There is almost no heat. Pressure has reached its maximum. Food is scarce, arriving only as the faintest trace of what exists above. Even the structure of the seafloor changes, sloping inward, forming a kind of natural funnel that draws material downward. It is not simply deeper, it is different. What makes this progression so important is not just the physical change, but what it represents. Each layer removes something life depends on. First light, then warmth, then energy, then abundance. By the time you reach the trench, the environment has stripped away nearly every condition that supports complex ecosystems on the surface. And yet, life does not vanish as these conditions disappear. It adapts, it persists, it reshapes itself to fit what remains. This is what makes the descent feel less like moving through space and more like moving through a series of broken assumptions. At each depth, something that seemed essential turns out not to be. The deeper you go, the less the surface world matters. Its rules fade, replaced by something quieter, slower, but no less real. And somewhere within that progression, a new question begins to form. If life can continue after losing light, after losing warmth, after losing its primary source of energy, then what does it actually need to survive? If life can continue after losing light, then the question is no longer where life exists, but what it is actually built on. Because on the surface, the answer feels simple. Almost everything alive depends, directly or indirectly, on the sun. Plants capture its energy, converting light into chemical fuel. Animals eat those plants, or eat other animals that rely on them. Even the air itself, the oxygen we breathe, is a byproduct of that same process. It creates the impression that sunlight is not just important, but foundational. Remove it, and the system collapses. That logic holds almost everywhere we can easily observe. Forests, oceans, deserts, even the smallest ecosystems trace their energy back to the same source. But as the descent continues beyond the reach of light, that connection is quietly broken. There is no photosynthesis in the deep ocean, no plants, no algae, no surface-driven production of energy. The entire system that dominates life above is absent, and yet life does not disappear with it. It changes its relationship with energy entirely. Instead of being generated locally, energy begins to arrive from somewhere else. Slowly, constantly, almost imperceptibly it falls. From the perspective of the surface, it looks like nothing. Tiny particles drifting downward through the water column, fragments of dead organisms, bits of waste, microscopic debris. But in the deep, this process becomes the primary source of sustenance. It is often called marine snow, though it has little in common with snow as we know it. It does not fall in flakes or accumulate evenly. It drifts, unevenly distributed, carried by currents, settling gradually onto the seafloor. Each particle is small, almost insignificant on its own. But over time they add up, a constant, delicate rain of organic material descending from the world above. For creatures living in the deep, this slow drift is not background noise. It is everything. It is the only reliable input of energy into a system that cannot produce its own. But it is not abundant. The deeper you go, the less of it arrives. Most of the material is consumed or broken down long before it reaches the trench. By the time it settles at the bottom, what remains is minimal, enough to sustain life, but only just. This creates a very different kind of ecosystem, one built not on growth and expansion, but on conservation. Every movement costs energy, every decision matters. Creatures cannot afford to waste anything. They feed slowly, metabolize slowly, live longer. Their entire existence is shaped by scarcity. This is not a place of competition in the way surface ecosystems are. It is a place of endurance. But marine snow, as constant as it is not the only source of energy. Occasionally something far more significant arrives, not gradually, but all at once. A sudden event that transforms the seafloor from one of the poorest environments on Earth into one of the richest, at least for a time. It begins at the surface, often unnoticed. A whale dies. It may be old or sick or injured. Its body, massive and dense, begins to sink. Unlike the particles that drift slowly downward, this descent is deliberate, driven by weight. Over the course of days, the carcass falls through the ocean, passing through layers that are each less capable of supporting life than the last. When it finally reaches the bottom, it does not simply settle, it changes everything. The arrival of a whale fall is one of the most dramatic events in the deep ocean. For a place defined by scarcity, it is an explosion of abundance. A single carcass contains more energy than the surrounding ecosystem might normally receive over years, even decades. The scent spreads quickly through the water, carried by faint currents. Creatures that would otherwise rarely encounter each other begin to gather. Scavengers arrive first, drawn by chemical signals. Amphipods swarm the body, covering it, feeding rapidly. Larger animals follow, consuming what they can. What was once a silent, empty stretch of seafloor becomes active, crowded, almost unrecognizable. But this is only the beginning. As the soft tissue is consumed, the system does not collapse back into scarcity. It transforms. The surrounding sediment becomes enriched with nutrients, supporting smaller organisms that feed on what remains. Bacteria multiply, breaking down what cannot be consumed directly. Over time, the carcass is reduced to bone, and even then the process continues. Inside those bones are lipids, energy stored in a form that can persist for years. Specialized organisms, some found nowhere else, colonize them. Worms burrow into the structure, relying on symbiotic bacteria to extract nutrients. Clams and other invertebrates settle nearby, forming communities that can last for decades. What began as a single death becomes an ecosystem in its own right, a temporary island of life in an otherwise sparse environment. And then, slowly, it fades. The nutrients are exhausted, the community disperses, the seafloor returns to its previous state, shaped once again by the slow, constant fall of marine snow. This cycle reveals something essential about life in the Mariana Trench. It does not rely on a steady, abundant energy source. It survives on unpredictability, on fragments, on leftovers, on rare events that provide brief moments of excess. It is a system that has adapted not to stability, but to interruption, to making the most of what arrives, whenever it arrives, and in doing so it breaks one of the most fundamental assumptions about life, that it requires a consistent local source of energy. In the trench, energy is distant, delayed, and minimal. It comes from above, from events that may have occurred thousands of meters away. It arrives in pieces, and unevenly distributed, often barely enough to sustain what depends on it, and yet life persists, not by overcoming these limitations, but by integrating them into its very structure. Every organism in this environment is shaped by this reality. Their bodies, their behavior, their entire existence is defined by the absence of what we consider essential. And that absence does not eliminate life. It transforms it into something slower, quieter, and far more resilient than it appears from the surface. What that means, over time, is that life in the trench is not defined by what it has, but by what it can afford to spend. Energy is not something to chase or compete for. It is something to conserve, to stretch, to use with restraint. And once you begin to see the deep ocean through that lens, the creatures that live there start to make a different kind of sense. They are not strange because they are extreme. They are strange because they are efficient. On the seafloor of the trench, movement is rare, and when it happens, it is deliberate. There is no urgency here, no need for speed, no advantage in sudden bursts of activity. Food does not run away. It arrives slowly, settles, and waits to be found. This changes the entire structure of behavior. Creatures do not hunt in the way we imagine predators hunting. They search, or they wait, or they respond when the environment changes. Amphipods are among the most common scavengers in these depths, and at first glance they appear simple. Small, pale, somewhat shrimp-like in form. But their simplicity is misleading. They are built for a world where every opportunity matters. When a source of food appears, they gather in large numbers, consuming it rapidly, storing what they can, then dispersing again into the sediment. Their bodies are adapted to process what little arrives, extracting as much energy as possible from material that, by the time it reaches them, has already been depleted. Between these rare moments of abundance, they exist in a state that is closer to waiting than living, conserving energy, minimizing movement, existing within the limits of what the environment provides. Sea cucumbers move even more slowly. If movement is the right word at all. They drift across the sediment, ingesting the mud itself, processing it internally, extracting organic material that is almost imperceptible in concentration. What they leave behind is cleaner sediment, slightly altered, a subtle reshaping of the seafloor that becomes visible only over long periods of time. Their bodies are soft, flexible, without rigid structure, not because they are primitive, but because rigidity is unnecessary. There is nothing here that demands strength or speed. There is only the need to endure. These organisms do not dominate their environment, they participate in it, quietly, continuously, shaping it through accumulation rather than force. And then there are the xenophyophores, which challenge the very idea of what a single organism can be. They do not move in any visible way. They do not hunt or chase or even react quickly to their surroundings. They exist as structures spread across the seafloor, sometimes the size of a human hand, sometimes larger, constructed from particles gathered from the environment itself. At first glance, they resemble small, fragile formations, almost like pieces of the sediment that have arranged themselves into patterns. But each one is a single cell, not a colony, not a network, but one continuous organism, extending outward to maximize contact with its surroundings. Their size is not a sign of complexity in the way we usually understand it. It is a strategy. In a place where nutrients are scarce, increasing surface area allows for greater access to what little is available. They collect particles, arrange them into protective structures, and use that framework to stabilize themselves in an environment where even the smallest disturbance can matter. They are both organism and architecture, built slowly, maintained over time, shaped by conditions that favor persistence over change. Around them, smaller organisms gather, using the structures as shelter, as a place where the otherwise featureless seafloor gains a small amount of complexity. In this way, even the simplest forms of life contribute to the structure of the ecosystem, not through action, but through presence. What becomes clear, looking at all of these organisms together, is that the trench is not a place of individual success. It is a system defined by limits. Every creature within it is constrained by the same fundamental problem. There is not enough energy to support excess. This creates a kind of quiet equilibrium. Life does not expand beyond what the environment can sustain. It adjusts itself to fit within those boundaries. Growth is slow, reproduction is infrequent. Lifespans may extend far beyond what we would expect for organisms of similar size in more active ecosystems. Time itself feels different here, stretched by the absence of urgency. Processes that would be rapid at the surface unfold gradually, almost imperceptibly. This is not a deficiency. It is a form of stability. In an environment where change is rare and resources are limited, speed becomes unnecessary. What matters is consistency, the ability to continue, to persist, to maintain function over long periods without requiring sudden inputs of energy. And this persistence is not passive, it is highly refined. Every aspect of these organisms, from their structure to their behavior, reflects a deep integration with the conditions they inhabit. Nothing is wasted, nothing is excessive. Even movement, when it occurs, is measured, efficient, aligned with the needs of the moment rather than driven by instinct alone. This creates an ecosystem that, while sparse, is remarkably resilient. It does not collapse when conditions fluctuate slightly. It does not depend on a constant influx of energy. It operates within narrow margins, but those margins are stable. Life here has adapted not to abundance, but to its absence, and in doing so it reveals something that is easy to overlook from the surface, that survival does not require richness, it requires balance. The ability to exist within limits without exceeding them, to function with less, not by struggling against scarcity, but by incorporating it into the very design of life. And as this pattern repeats across species, across depths, across the entire trench, another realization begins to emerge, that these organisms are not simply enduring the environment, they are shaped by it in ways that go far beyond behavior or form, because at a certain depth, survival is no longer just about what a creature does, it becomes about what it is at the most fundamental level. Because at a certain depth, the problem is no longer just finding enough energy to survive. It becomes something more fundamental than behavior or strategy. It becomes chemical. The pressure in the trench does not simply push against the outside of a body. It reaches inward, affecting the very molecules that allow life to function at all. Proteins, which are responsible for nearly every process inside a living organism, rely on precise three-dimensional shapes to do their work. They fold in specific ways, creating structures that can bind to other molecules, trigger reactions, carry signals. But under extreme pressure, those shapes begin to change. They distort, collapse, lose their function. Enzymes stop working. Cellular processes fail. For most forms of life, this happens long before reaching the depths of the Mariana Trench. It is not a dramatic failure. It is quiet, systemic, a gradual unraveling of the mechanisms that sustain life. This is why, for a long time, scientists believed that vertebrates could not exist at these depths. Creatures with complex nervous systems, with structured proteins, with the kind of internal organization that defines fish and mammals and birds, seemed fundamentally incompatible with the conditions of the Hadal zone. It was not just a question of pressure tolerance, it was a question of biochemical stability. The deeper you go, the more those systems should fail. And yet, when cameras finally reached these depths and began to observe the seafloor in detail, something appeared that did not fit that understanding at all. A fish. Not a distant relative, not an ambiguous shape, but a clearly identifiable vertebrate, moving slowly just above the sediment. Pale, almost translucent, its body soft and flexible, lacking the rigid structure we associate with fish in shallower waters. It did not look powerful. It did not look particularly adapted in any obvious way. If anything, it looked fragile, as though it belonged in a much less demanding environment. But it was there, functioning, surviving, existing at depths where it should not have been able to. This animal, now known as the Hadal snailfish, represents one of the most important biological discoveries in the deep ocean. Not because of how it looks, but because of what it implies. It is a vertebrate living near the absolute limit of what vertebrate life can tolerate. And to do so, it has not simply adjusted its behaviour, it has rewritten its internal chemistry. The snailfish's body is built around the same basic structures as other fish, but those structures are altered in subtle, critical ways. Its bones are reduced, lighter, less mineralized. Hard, rigid skeletons become a liability under pressure, creating points of weakness where forces can concentrate. Instead, the snailfish relies on a softer framework, one that compresses evenly, distributing pressure rather than resisting it. Its tissues are gelatinous, with a density close to that of the surrounding water, allowing it to maintain position without expending energy. But the most important changes are not visible from the outside. They occur at the molecular level. Within the cells of the snailfish are compounds that act as stabilizers, protecting proteins from the effects of pressure. One of the most significant of these is trimethylamine N-oxide, or TMAO. This molecule is present in many marine animals, but in the snailfish, it exists in much higher concentrations. Its role is to counteract the destabilizing effects of pressure, allowing proteins to maintain their functional shapes even under extreme compression. Without it, the internal systems of the fish would begin to fail. With it, those systems continue to operate, even at depths where they should collapse. This adaptation comes with its own limits. The concentration of TMAO increases with depth, and beyond a certain point it becomes chemically problematic. There is a boundary where the conditions required to stabilize proteins begin to interfere with other processes. This is why the snailfish represents not just a success, but a threshold. It exists near the edge of what is biochemically possible for vertebrates. Go deeper, and even these adaptations may no longer be enough. What makes this so compelling is that it challenges a deeper assumption about life, that there are fixed limits, clearly defined boundaries beyond which certain forms cannot exist. The snailfish does not ignore those limits. It approaches them, adapts to them, reshapes itself to operate within them. It does not resist the environment, it becomes part of it. And in doing so, it reveals that what we think of as constraints are often more flexible than they appear. The existence of this animal is not just a curiosity, it is evidence that life can modify itself at a level that goes far beyond surface adaptation. It can change its chemistry, its structure, its internal balance, to match conditions that would otherwise be destructive. It suggests that the limits of life are not defined by the environment alone, but by the ability of organisms to adjust to that environment over time. And this raises a question that extends beyond the trench itself. If a vertebrate can survive here, at pressures that disrupt fundamental biological processes, then where exactly is the boundary? How extreme can conditions become before life can no longer adapt? The snailfish does not answer that question. It complicates it. It shows that the line is not where we expected it to be, that the point at which life should stop is not always the point at which it does. And as more observations are made, as more species are studied, that line continues to shift. Not dramatically, not suddenly, but steadily. As each new discovery adds another exception to the rules we thought were fixed. In the trench, survival is not about overcoming the environment. It is about becoming compatible with it at every level, from behaviour to biology to chemistry. The snailfish is not an outlier in that sense. It is a clear example of a pattern that repeats throughout the deep ocean. Life does not break the rules of science here. It reveals that those rules were never as rigid as we believed. And if life can reshape its chemistry to survive pressure, it can also reshape something far more immediate, something that defines how organisms interact with one another in the first place. Because in a world without light, visibility should not matter. There is no background to blend into, no colour to hide within, no shadows to disappear behind. At first, it seems like camouflage itself becomes unnecessary. But the deeper ocean does not remove the need to avoid being seen. It changes what being seen actually means. In the absence of sunlight, vision does not disappear entirely. It evolves. Many creatures produce their own light, brief flashes or steady glows that cut through the darkness in ways that feel almost deliberate. These signals reveal shapes, movement, presence, and where there is visibility, even if it is artificial, there is still the need to hide. But hiding here does not rely on colour or pattern. It relies on something more complete, the removal of visibility altogether. Some of the most remarkable organisms in the deep ocean are not defined by what they show, but by what they do not. Their bodies are transparent, almost entirely invisible, allowing light to pass through them with minimal distortion. This is not partial camouflage. It is near erasure. At a glance, they appear absent, their outlines only visible when they move or when a faint reflection reveals the edges of their form. It is an adaptation that feels counterintuitive at first. Transparency seems fragile, exposed, lacking protection. But in this environment, it is one of the most effective ways to avoid detection. If there is no surface to reflect light, nothing to cast a silhouette, then there is very little to see. The glass squid is one of the clearest examples of this strategy. Its body is almost entirely transparent, its internal organs reduced or arranged in ways that minimize visibility. Only the eyes remain prominent, suspended within an otherwise invisible structure. They appear almost detached, floating in the water, disconnected from any body. It creates an image that feels incomplete, as though something is missing. But nothing is missing. The animal is simply designed to avoid being perceived as a whole. Movement too is altered. Instead of rapid, obvious motion, many of these organisms drift or pulse gently, minimizing disturbances in the water. Sudden movement creates contrast, and contrast creates visibility. By reducing speed, by aligning their motion with the surrounding currents, they remain difficult to detect even when they are not perfectly still. It is not just about appearance, it is about behavior that complements that appearance. This combination of form and movement creates a kind of partial disappearance. Not complete invisibility, but enough to avoid attention in an environment where encounters are rare, and detection can mean the difference between survival and consumption. And this adaptation is not limited to a single species. It appears across multiple groups, from jelly-like organisms to small fish to various forms of plankton. Each has arrived at a similar solution through different evolutionary paths. Remove colour, reduce structure, allow light to pass through, become something that does not interrupt the environment. What makes this even more striking is that it represents a reversal of what we often associate with evolution. On the surface, complexity tends to increase. Structures become more defined, more specialized, more visible. In the deep ocean, in certain cases, evolution moves in the opposite direction, toward reduction, toward simplification, toward forms that are less present rather than more. It is not about becoming stronger or faster, it is about becoming less noticeable, and this creates a strange effect. These organisms are fully functional, fully adapted, yet they appear incomplete, as though they are in the process of fading out of the world rather than becoming more firmly part of it. Their transparency is not just physical, it feels conceptual, a shift away from the idea that survival requires presence. In this environment, survival can mean the opposite: to exist without being observed, to move without leaving a trace, to interact without drawing attention. This strategy extends beyond individual organisms. Entire layers of the deep ocean are filled with creatures that are difficult to perceive, not because they are rare, but because they are designed to be overlooked. The water is not empty. It is occupied by forms that do not announce themselves. This changes how we understand density, abundance, even the idea of an ecosystem. It is not always about what is visible, it is about what is there, regardless of whether it can be easily seen. And this raises an interesting possibility, that in some environments, the most successful forms of life are not the ones that dominate the space around them, but the ones that integrate into it so completely that they become almost indistinguishable from it. Not by blending in, but by removing the features that would make them stand out in the first place. In the context of the trench, where energy is scarce and encounters are infrequent, this approach makes sense. Avoiding detection reduces the need for defense. It minimizes conflict. It allows organisms to exist with less expenditure of energy, aligning with the broader pattern of conservation that defines life at these depths. And when combined with the chemical adaptations seen in organisms like the snailfish, it becomes clear that survival in the deep ocean is not achieved through a single strategy. It is a layered process. Physical structure, internal chemistry, behavior, we all working together to maintain a balance within an environment that offers very little room for error. Transparency, in this sense, is not just a visual trait. It is part of a larger shift in how life expresses itself, a move away from visibility, from presence, from the need to interact with light in the ways we are familiar with. It is an adaptation that feels almost philosophical, a quiet answer to a very simple problem. If being seen is a risk, then the most effective solution is not to hide better. It is to become something that is no longer easily seen at all. But invisibility is only one way to avoid being seen. In a place where light no longer exists naturally, another strategy emerges, one that seems almost contradictory at first. Instead of disappearing, some creatures create their own visibility, not to reveal themselves, but to control how and when they are perceived. In the deep ocean, darkness is not simply an absence. It is a medium, something that can be shaped, interrupted, used. And the organisms that live here have learned to manipulate it with remarkable precision. Bioluminescence is one of the most widespread adaptations in the deep sea, and yet it is often misunderstood as something decorative, almost accidental, a byproduct of chemistry rather than a deliberate tool. In reality, it is anything but passive. It is a language, a weapon, a signal, and in many cases, be a form of control over an environment that would otherwise remain completely uniform. The light produced by these organisms is not constant. It appears suddenly, often in brief flashes or pulses, then disappears just as quickly. This intermittent quality is essential. A continuous glow would make an organism visible at all times, turning it into a fixed point in an otherwise dark environment. But a flash can be timed, directed, used in specific moments. It can confuse, attract, distract. It allows the organism to choose when it exists visually and when it does not. Some species use this light defensively. When threatened, they release bursts of luminescent material into the water, creating a cloud of glowing particles that obscure their escape. The effect is disorienting, not just because it produces light, but because it breaks the uniformity of the darkness in a way that predators are not adapted to process quickly. In that brief moment of confusion, the organism moves away, returning to invisibility. Others use bioluminescence as a lure. The anglerfish is one of the most well-known examples, though its significance goes beyond its appearance. Suspended in the darkness, it carries a small appendage extending from its head, tipped with a glowing organ. This light is not bright, not enough to illuminate the surroundings, but enough to be noticed by organisms drifting nearby. In a world where energy is scarce, even the suggestion of food is enough to draw attention. Smaller creatures approach, guided by the faint glow, unaware that what they are moving toward is not a source of sustenance, but a predator waiting without movement. The anglerfish does not chase, it does not pursue. It waits, conserving energy, allowing the environment to bring food to it. The light is not a signal of presence, it is a trap, carefully calibrated to attract without revealing too much. This kind of strategy depends on precision. Too much light, and the illusion breaks. Too little, and it fails to attract anything at all. It is a balance that has been refined over time, shaped by the same constraints that define every other aspect of life in the deep. But perhaps the most striking use of light is found in organisms that produce wavelengths that are effectively invisible to most other species. The dragonfish, for example, emits light in the red spectrum, a range that does not travel far in water and is not detected by the visual systems of many deep-sea creatures. This creates a kind of private illumination. To most organisms, the environment remains dark, but to the dragonfish, it is partially visible. It can see without being seen. This is not just an adaptation. It is an advantage that exists outside the normal rules of perception in this environment. It allows for a form of asymmetry, where one organism has access to information that others do not. In a place where visibility is rare and valuable, this difference can determine survival. Light, in this context, is no longer just a tool for interaction. It becomes a way of reshaping the environment itself, creating localized conditions that differ from the surrounding space. It introduces complexity into what would otherwise be a uniform darkness, and because it is produced by living organisms, that complexity is dynamic, constantly changing, appearing and disappearing in patterns that are not immediately predictable. This transforms the deep ocean into something far more active than it appears. It is not empty, not static, not silent. It is filled with signals, with brief flashes of information, with interactions that occur too quickly or too subtly to be easily observed. The absence of sunlight does not remove visibility entirely. It decentralizes it, placing it in the control of the organisms themselves. And this creates a kind of hidden network of communication and interaction. one that operates on entirely different principles from the surface world. There is no ambient light to define the environment. There are only individual sources, each one serving a specific purpose, each one appearing only when needed. What makes this particularly compelling is that it represents a shift in how life interacts with its surroundings. On the surface, organisms respond to light. In the deep, they generate it. They do not adapt to illumination, they create it, shaping their interactions in ways that are precise, intentional, and often invisible to anything that is not directly involved. This level of control suggests something deeper about life in the trench and the surrounding depths. That survival is not just about enduring conditions or adapting to limitations. It is about finding ways to operate within those limitations that create new possibilities. Light, which is absent in its natural form, is reintroduced in a controlled, selective way, allowing organisms to regain some of the functions that would otherwise be lost. And in doing so, they do not simply replicate what exists at the surface, they develop entirely new ways of using it. In this environment, darkness is not a barrier. It is a resource, something that can be shaped and used, something that organisms can move within without being constrained by it. And the light that appears within it is not a return to what was lost. It is something different, something more deliberate, designed not to illuminate the world, but to influence it in very specific ways. And once light becomes something that can be created rather than depended on, the idea that life must ultimately trace itself back to the sun begins to weaken. Because even the strategies we have seen so far, the drifting particles, the whale falls, the faint rain of organic material, all still originate from the surface. They are delayed, fragmented, diminished, but they are still connected to sunlight in some distant way. The deeper question is whether that connection is necessary at all, whether life requires the sun not just as a convenience, but as a foundation. For a long time, the assumption was that it did, that no matter how indirect the pathway, energy had to begin with light. It was a simple, elegant model, and it worked almost everywhere it was tested. But deep beneath the ocean, in places where the seafloor is not flat and quiet but fractured and active, something else exists, not drifting down from above but emerging from below. Hydrothermal vents form where the Earth's crust is thin or broken, allowing seawater to seep downward into the planet itself. As it descends, it encounters heat generated by magma, warming rapidly, reacting with minerals, dissolving elements that are otherwise locked within the rock. This superheated fluid, now chemically altered, rises again, forced back toward the seafloor where it emerges through openings in the crust. When it meets the surrounding water, the difference is extreme. Temperatures can exceed hundreds of degrees near the vent itself, though the pressure prevents the water from boiling. Minerals precipitate out of the fluid, forming towering structures that grow slowly over time, like chimneys rising from the seafloor. The environment around these vents is unstable, chemically rich, and completely isolated from sunlight, and yet it supports life. Not in the sparse, slow-moving way seen in the surrounding sediment, but in dense, active communities that cluster around the vent openings. At first, this seems contradictory. The trench is defined by scarcity, by the slow arrival of energy from above. But here, energy is not arriving. It is being generated locally through chemical processes that do not involve light at all. The foundation of these ecosystems is not photosynthesis, but chemosynthesis. Instead of using sunlight to convert carbon dioxide into organic material, certain bacteria use chemical energy, derived from compounds like hydrogen sulfide, to perform a similar function. They build organic molecules not from light, but from the reactions taking place within the Earth itself. This is not a variation of the surface model. It is a different system entirely, and it forms the base of a complex ecosystem. Around these bacteria, other organisms gather, forming relationships that are both intricate and highly specialized. Tube worms are among the most recognizable inhabitants of these environments, though their appearance alone does not explain their significance. They do not have mouths or digestive systems in the conventional sense. Instead, they rely on symbiotic bacteria housed within their bodies. These bacteria perform chemosynthesis, producing organic compounds that the worms can use as a source of energy. In return, then the worms provide access to the chemicals the bacteria need, drawing in water rich in hydrogen sulfide and oxygen through specialized structures. It is a partnership that blurs the line between organism and environment, between individual and system. Neither can survive without the other. Together they form a unit that is capable of existing in conditions that would otherwise be uninhabitable. Surrounding them are other species, clams, shrimp, crabs, each adapted in their own way to the unique chemistry of the vents. Some host bacteria within their tissues, others feed on the bacterial mats that form around the vent openings. The density of life in these areas can be surprisingly high, especially when compared to the sparse distribution found in the surrounding deep sea. It is not abundance in the sense of surface ecosystems, but it is concentrated, localized, sustained by a continuous flow of chemical energy rather than a distant intermittent source. What makes this system so significant is not just that it exists, but that it operates independently of the sun. It is powered by the Earth itself, by heat and chemistry, by processes that occur far below the surface. This challenges one of the most fundamental assumptions about life, that it requires a connection to light, even if that connection is indirect. Here, that connection is absent, and yet life is not only present, but active, structured, organized. It suggests that the requirements for life are broader than we once believed. That energy does not need to come from a single source, that the pathways through which it is accessed can vary, as long as the underlying chemistry supports it. In the context of the trench, this adds another layer to the understanding of how life persists. It is not limited to what falls from above. It can also emerge from below, from the planet itself. And this duality, energy arriving from the surface, energy generated within the Earth, creates a more complex picture of the deep ocean than one defined solely by scarcity. It is not uniformly poor in resources. It is uneven, with pockets of relative abundance shaped by geological activity. These vent systems are not permanent. They shift, change, become active or inactive over time. The communities that depend on them must adapt to these changes, relocating, reforming, responding to conditions that are dynamic rather than stable. This introduces a different kind of challenge, one not based on scarcity alone, but on variability. Yet life here is not only efficient, it is responsive, capable of adjusting to an environment that is both extreme and unpredictable. And as these discoveries accumulated, they began to influence not just the study of the deep ocean, but the broader understanding of life itself. If ecosystems can exist without sunlight, if they can be sustained by chemical energy alone, then the range of environments that can support life expands significantly. It is no longer limited to the surface of planets, to regions where light is available. It can extend into subsurface oceans, into places where heat and chemistry provide the necessary conditions. The trench and the systems within it become more than just an isolated curiosity. They become a model, a demonstration of what is possible when life is not constrained by the assumptions formed at the surface. And in that sense, they do not just break the rules, they reveal that the rules were incomplete. Once it becomes clear that energy can emerge not only from above but from deep within the Earth itself, the Mariana Trench begins to feel less like a static place and more like a process in motion. What appears, at first glance, to be a silent, frozen environment is in reality part of one of the most active systems on the planet. The stillness is deceptive. Beneath the calm surface of the seafloor, forces are constantly reshaping the structure of the Earth, slowly but relentlessly. The trench exists because the planet is not fixed. It is dynamic, layered, and in constant transition, even if those changes unfold over timescales far beyond human perception. The Mariana Trench sits along a boundary between two massive tectonic plates, the Pacific Plate and the smaller Mariana Plate. These are not rigid, unmoving structures, but vast sections of the Earth's crust that shift, interact, and sometimes collide. In this region, the Pacific Plate is being forced downward, sliding beneath the Mariana Plate in a process known as subduction. It is not a dramatic event. There is no sudden collapse, no visible rupture. Instead, it is a slow descent, measured in centimeters per year, where one piece of the planet is gradually pulled into the interior. Over time, this movement creates the trench itself, a long, curved scar in the ocean floor that marks the boundary between what remains above and what is being drawn below. This continuous motion means that the trench is not a fixed structure. It is being formed, deepened, and reshaped at all times. Sediments from the ocean above are carried downward, compressed, and altered as they descend. Organic material, including the remains of organisms that once lived near the surface, is pulled into an environment where pressure and temperature steadily increase. Water trapped within the rock is released through chemical reactions, influencing the surrounding geology and contributing to processes that can extend far beyond the trench itself. What seems like a distant, isolated environment is in fact connected to a larger planetary system that cycles material between the surface and the deep interior. The effects of this movement are not always visible, but they are constant. Stress builds along the boundary between the plates, accumulating over time as friction resists their motion. Eventually, that stress is released in the form of deep earthquakes, some occurring at depths far below what we would normally associate with seismic activity. These are not the earthquakes that disrupt cities or reshape coastlines. They occur far beneath the ocean floor, often unnoticed by anything other than sensitive instruments. But their existence reveals something important. Even at these extreme depths, where pressure is immense and conditions seem stable, the Earth is still shifting. The trench is not insulated from the planet's internal dynamics. It is one of the places where those dynamics are most clearly expressed. This introduces a different kind of unpredictability into an environment already defined by extremes. Life here is not only dealing with pressure, darkness, and scarcity. It is also existing within a landscape that is slowly changing beneath it. The seafloor itself can shift, fracture, or deform over time, altering the distribution of sediment, the flow of nutrients, i.e. the structure of habitats. These changes are gradual, but they are persistent, adding another layer of complexity to an ecosystem that is already operating at the limits of what is possible. Even the hydrothermal systems that support localized communities are tied to this tectonic activity. The vents form where the crust is fractured, where seawater can penetrate and interact with the heat below. As the plates move, these fractures can open, close, or shift, changing the locations where energy emerges. Entire ecosystems may develop around a vent only to disappear when the activity ceases, forcing the organisms that depend on it to adapt, relocate, or vanish. This is not a stable environment in the conventional sense. It is a system defined by both scarcity and change, where life must be prepared not only to survive with limited resources, but to respond to a landscape that is never entirely fixed. The deeper implication of this is that the trench is not simply a place where life endures extreme conditions. It is a place where those conditions are actively being generated by the planet itself. The pressure, the depth, the chemical environment, all are products of processes that are ongoing. The trench is not separate from the Earth's internal activity. It is one of its visible expressions, a boundary where surface and interior meet. This changes how the environment should be understood. It is not a passive backdrop against which life exists. It is an active participant in shaping what that life becomes. Organisms here are not just adapting to a set of fixed conditions. They are interacting with a system that is continuously evolving, even if that evolution is slow. Over time, these interactions create a balance, not a static equilibrium, but a dynamic one, where life and environment influence each other in subtle ways. The trench, then, is not silent. It does not need to produce visible motion or sound to be active. Its activity is embedded in its structure, in the slow movement of plates, in the release of energy, in the constant reshaping of the sea floor. It is a reminder that even in the deepest, darkest parts of the ocean, far removed from the surface, the Earth is not still. It is always in the process of becoming something else. Long before cameras could drift silently through the trench and transmit images back to the surface, reaching these depths required something far more uncertain. It required entering the environment directly, placing human life inside a structure that had to withstand conditions no human body ever could. The idea itself was difficult to justify. The risks were not fully understood, the margin for error almost non-existent, and the environment offered no forgiveness. But the desire to reach the deepest point on Earth was not driven only by curiosity. It was driven by the need to see, to confirm, to replace assumption with observation. In 1960, that attempt took form in a vessel called Trieste, a bathyscaphe designed not for speed or maneuverability but for descent. It consisted of a spherical pressure chamber attached to a large float filled with gasoline, chosen not for its fuel properties, but because it is less dense than water and incompressible at depth. The sphere itself was small, just large enough to hold 2 people, constructed from thick steel walls designed to resist the immense pressure waiting below. Inside that sphere, Jacques Picard and Don Walsh prepared to descend into a place no human had ever reached. The journey downward was slow, taking several hours as the craft sank steadily through the layers of the ocean. At first, the descent would have felt familiar, light filtering through the water, a gradual dimming rather than a sudden change. But as they passed beyond the reach of sunlight, the outside world disappeared entirely. The small window in the sphere no longer revealed a landscape, only darkness. There were no reference points, no sense of movement except what could be inferred from instruments. The feeling of descent became abstract, detached from direct experience. Inside the sphere, space was limited. Movement was restricted. Every sound, every vibration carried meaning, because each one could indicate stress on the structure, a potential failure point. The pressure outside increased continuously, pressing inward with a force that could not be felt directly, but was always present. It was not like being underwater in a conventional sense. There was no sensation of immersion. Instead, there was a growing awareness that everything outside the sphere was hostile, that the boundary between safety and destruction was defined entirely by the integrity of the vessel. As the descent continued, that awareness sharpened. The deeper they went, the less certain the outcome became. Calculations could predict the pressure, the materials had been tested, but no one had remained at those depths long enough to fully understand what might happen over time. The environment was not just extreme, it was unfamiliar. And then, partway through the descent, something happened that would remain one of the most unsettling moments of the journey. A loud cracking sound echoed through the sphere. It was sudden, sharp, unmistakable. In an environment where structural failure would be immediate and irreversible, that sound carried a very specific implication. For a moment, there was no way to know what had caused it, whether it was a minor adjustment in the materials or the beginning of something more serious. The descent paused. The situation was assessed as best as it could be, given the limited information available. There were no external cameras, no way to inspect the outside of the vessel, only the instruments, the structure itself, and the judgment of the two men inside. After some time, the decision was made to continue. The crack, it was later understood, had come from an outer component, not the pressure sphere itself. But at that moment, certainty was impossible. What followed was not just a continuation of the descent, but a commitment to it, an acceptance that the only way forward was deeper into an environment that had already demonstrated its capacity to challenge the limits of their equipment. When they finally reached the bottom, after nearly 5 hours, the nature of the experience changed again. The descent stopped. The sphere settled into the sediment, raising a cloud of fine particles that reduced visibility even further. For a brief period, the outside world was not just dark but obscured, filled with suspended material that drifted slowly back down. As it cleared, the seafloor became visible, not as a dramatic landscape but as a flat, quiet expanse. There were no towering structures, no obvious signs of movement, just sediment stretching outward into darkness. But even in that stillness, something unexpected appeared. A small, pale shape moved across the seafloor, resembling a flatfish or some other form of vertebrate life. It was not large, not prominent, but its presence carried significance far beyond its size. Because according to the understanding at the time, such an organism should not have been able to exist at that depth. The observation was brief, and it would later be questioned, debated, reconsidered as more information became available. But in that moment it represented something important. Not a definitive answer, but a challenge to what was believed to be possible. The time spent at the bottom was limited, less than an hour, constrained by the need to return safely to the surface. The ascent was faster than the descent, but it carried its own uncertainties. The vessel rose slowly, retracing the path upward, leaving behind a place that, despite being briefly visited, remained largely unknown. What that journey demonstrated was not just that the trench could be reached, but that reaching it required more than technology. It required entering an environment that does not accommodate human presence, that resists it at every level. The pressure, the isolation, the lack of visibility all contribute to a sense that this is not a place meant to be inhabited, even temporarily. And yet, that descent marked the beginning of a shift. From assumption to observation, from theory to experience. It didn't answer all questions. In many ways, it created new ones. But it established something fundamental. That even in the most extreme environments on Earth, direct exploration is possible, even if it is difficult, even if it reveals more uncertainty than clarity. What remained after that descent was not just the fact that humans had reached the bottom, but the uncertainty that followed what they thought they had seen. The observation itself was simple. A small, pale organism moving across the seafloor resembling a fish. Not a drifting shape, not an ambiguous form, but something with movement that suggested intention, structure, familiarity. In any other environment, the sight would not have been remarkable. Fish exist across vast regions of the ocean, adapting to different depths, different conditions. But at nearly 11 kilometers below the surface, the context changes everything. Because at that depth, according to the understanding at the time, such a creature should not exist at all. The problem was not visibility, it was compatibility. The pressure at the bottom of the Mariana Trench is so extreme that it interferes with the basic chemistry of vertebrate life. Proteins lose their structure, cellular processes begin to fail, membranes become unstable. These are not minor challenges that can be overcome with simple adaptation. They represent fundamental limits on how biological systems can function, or at least that is what the model suggested. The deeper the environment, the narrower the range of possible life forms. And beyond a certain point, vertebrates, animals with complex internal systems, were expected to disappear entirely. So when Picard described seeing what appeared to be a flatfish on the seafloor, it introduced a contradiction. Not just a surprising observation, but one that directly challenged the theoretical boundary of life. At first, the report was taken seriously. It was the only direct observation from that depth, made by individuals who had just completed an unprecedented descent. There was no immediate reason to dismiss it, but as time passed, and as more data became available, the interpretation began to shift. Scientists started to question whether what had been seen was truly a fish, or something else entirely. The conditions during the observation were far from ideal. When the Trieste reached the bottom, it disturbed the sediment, creating a cloud of fine particles that reduced visibility. Light was limited to what the submersible could produce. Shapes would have appeared indistinct, edges blurred, movement harder to interpret. In that environment, perception is not always reliable. The brain attempts to make sense of incomplete information, often filling in gaps based on familiar patterns. A moving shape on the seafloor might resemble a fish, not because it is one, but because that is the closest match the mind can construct from what little it can see. As remotely operated vehicles began to explore the trench in later decades, the evidence did not support the presence of flatfish at those depths. Instead, they found other organisms, invertebrates, small, soft-bodied creatures adapted to the pressure in ways vertebrates typically are not. The deepest confirmed fish were found at slightly shallower depths, still extreme, still near the limits of what is possible, but not quite at the bottom itself. This led to a reinterpretation of the original observation, that what had been seen may not have been a fish at all, but a type of sea cucumber or another organism whose shape, under low visibility, could be misidentified. The controversy was not resolved with a single piece of evidence. It evolved gradually as new observations accumulated, as models of deep-sea biology became more refined, as understanding of pressure adaptation improved. And yet, the original sighting remains part of the story, not because it is confirmed, but because it illustrates something essential about exploration at these depths. That even direct observation is subject to uncertainty. The trench does not present itself clearly. It does not offer easily interpretable data. It exists in conditions that distort perception, limit visibility, and challenge the reliability of what is seen. This creates a tension between observation and interpretation, between what appears to be present and what can be supported by evidence. In most environments, these two align closely, but in the trench, they can diverge. What is seen may not be what is actually there, and what is actually there may not be easily seen at all. This uncertainty is not a flaw in the process. It is part of the environment itself. The deeper the exploration goes, the more it encounters conditions that were not part of the assumptions used to build our understanding of life. And when those assumptions are challenged, the first response is often to question the observation, to reconcile it with existing models. But sometimes the observation is what forces the model to change. In the case of the Mariana Trench, both processes have occurred. Some sightings have been reinterpreted, refined, corrected. Others have led to new discoveries, new understandings of what life can tolerate. The boundary between possible and impossible has shifted not in a single moment, but through a series of adjustments, each one informed by new data, new perspectives. The sighting from the Trieste sits at the intersection of these processes. It is not fully accepted, not fully dismissed. It remains unresolved, a point of ambiguity in a place defined by extremes, and that ambiguity reflects a larger truth about the trench itself, that it is not fully known, not fully mapped in terms of its biological or physical characteristics. It is still being explored, still revealing new information, still challenging the frameworks used to understand it. In this context, uncertainty is not a limitation. It is a signal that there is more to learn, more to observe, more to question. The trench does not offer clear answers. It offers fragments, glimpses, observations that must be interpreted carefully, often revised, sometimes reconsidered entirely. And this process, slow, methodical, ongoing, is what gradually builds a more accurate picture of what exists at these depths. But that picture is never complete. It is always subject to change, to refinement, to the possibility that something new will be discovered that does not fit within what is already known. Uncertainty is expected in a place like this. The trench hides more than it reveals, and even direct observation can leave room for interpretation. But there are some discoveries that do not depend on interpretation at all. They are clear, unmistakable, and difficult to reconcile with what the trench is supposed to represent. Because for a long time, places like the Mariana Trench were thought of as untouched, not because they were protected or deliberately preserved, but because they were inaccessible, too deep, too remote, too extreme for human influence to reach them in any meaningful way. It was a convenient assumption, one that suggested that even as the surface of the planet changed, there were still environments that remained separate, isolated from the effects of human activity. The trench, with its depth and its distance from everyday life, seemed like one of those places, a final boundary beyond which our presence did not extend. But that assumption, like many others about the deep ocean, did not hold. As exploration improved, as remotely operated vehicles began to survey the seafloor with greater detail, something began to appear in the images that did not belong to the environment at all. Not organisms, not geological formations, but objects that could be traced back to the surface. Fragments of plastic, pieces of synthetic material, items that had no natural origin in the deep ocean. At first, these findings were isolated, unexpected. A single piece of debris resting on the sediment, an anomaly rather than a pattern. But over time, the observations became more frequent. Different expeditions, different locations, similar results. The presence of human-made material at depths where human beings themselves had only briefly visited. The realization was gradual, but once it became clear, it was difficult to ignore. The trench was not isolated. It was connected to the surface in ways that extended beyond energy and organic material. The same processes that carry marine snow downward, that transport nutrients and organic debris, also carry the byproducts of human activity. Plastic, in particular, behaves in ways that make it especially persistent. It does not degrade easily. It breaks into smaller pieces, but those pieces remain, circulating through the water column, eventually settling on the seafloor. Some of it sinks directly, weighed down by attached organisms or trapped air that escapes over time. Some of it is ingested by marine life. You move through biological systems redistributed in ways that are not immediately visible. The pathways are complex, but the outcome is consistent. Material introduced at the surface does not remain there. It moves, slowly but continuously, into deeper regions, even into the trench. What makes this particularly striking is the contrast. The Mariana Trench is one of the most extreme environments on Earth, defined by pressure, darkness, and isolation. And yet, within that environment, objects exist that are entirely out of place, shaped by processes that occur far above, introduced without intention, carried downward by mechanisms that do not distinguish between natural and artificial. A plastic bag resting on the seafloor at nearly 11 kilometers depth is not just an object. It is evidence of a connection that was not fully understood, a demonstration that remoteness does not guarantee separation, that even the most distant environments are linked to what happens at the surface. This connection extends beyond visible debris. Microplastics, particles too small to be easily seen, have been detected in deep-sea sediments and within the bodies of organisms that live there. These particles originate from larger materials that have broken down over time, dispersing throughout the ocean, entering systems that were never designed to process them. Their presence is more difficult to observe directly, but their impact is potentially more widespread. They can be ingested, accumulate within tissues, interact with biological processes in ways that are still being studied. The trench, which was once thought to be beyond the reach of such influence, is now part of that broader system. This introduces a different kind of tension into the understanding of the deep ocean. Up to this point, the trench has been a place where natural limits are tested, where life adapts to conditions that seem incompatible with its existence. The challenges are environmental, chemical, physical. But this is something else. Not a natural constraint, but an external addition. A layer of complexity introduced not by the Earth, but by human activity. It does not replace the existing challenges. It adds to them in ways that are not always immediately visible, not always fully understood. The phrase, "our waste arrived before us," captures this shift in a way that is difficult to ignore. Humans reach the bottom of the trench only a handful of times, but the materials produced by human society have reached it far more frequently, and they are carried downward over time, accumulating in places where direct human presence is rare. It is a reversal of expectation. Exploration usually precedes impact. In this case, impact has preceded sustained exploration. This does not mean that the trench is overwhelmed by pollution. It remains an extreme environment, largely defined by its natural conditions, but the presence of human-made material changes how it is perceived. It is no longer possible to think of it as completely separate, completely untouched. It is part of the same system as the rest of the ocean, subject to the same flows, the same exchanges, the same long-term processes that connect surface and depth. And this realization carries implications that extend beyond the trench itself. It suggests that there are no truly isolated environments on Earth, no places that are entirely removed from the influence of what happens elsewhere. The connections may be slow, indirect, difficult to trace, but they exist. Over time, they become visible, not through dramatic change, but through accumulation, through the presence of something that does not belong, appearing in a place where it should not be. The idea that nothing is truly untouched leads to a deeper realization about the trench, one that goes beyond biology or human impact and reaches into the behavior of matter itself. Because at these depths, it is not only life that changes. The physical world begins to behave in ways that feel unfamiliar, even when the underlying principles remain the same. The rules have not been broken, but the conditions are so far removed from everyday experience that the results appear almost contradictory. Pressure is the defining factor. It is constant, immense, and unavoidable, influencing every interaction at every scale. At the surface, pressure is something we rarely consider. It exists, but it does not dominate our perception. Materials behave in predictable ways. Liquids flow, gases expand. Solids retain their shape unless acted upon by force. These expectations are built from experience, from a narrow range of conditions that feel normal because they are familiar. But in the trench, those expectations begin to fail. Carbon dioxide, for example, behaves differently under extreme pressure. At the surface, it is a gas, invisible, dispersing easily into the atmosphere. under certain conditions, it can become a liquid, but those conditions are specific, requiring both pressure and temperature to align. In the deep ocean, those conditions are not unusual. They are constant. There are locations where liquid carbon dioxide can accumulate on the seafloor, forming pools that resemble bodies of water, but are fundamentally different in composition. These pools do not mix easily with the surrounding seawater. They sit within it, and denser, more stable under pressure, creating boundaries that are not immediately visible but are very real. Organisms that encounter these pools experience them not as water, but as a distinct environment, one that can be toxic, disruptive, incompatible with their biology. The existence of liquid CO2 at the seafloor challenges intuition, not because it violates physical laws, but because those laws are operating under conditions we do not regularly observe. It is a reminder that the states of matter we consider standard are dependent on context. Change the context, and the behavior changes with it. This applies not only to gases and liquids, but to solids as well. Materials that are rigid at the surface may become more flexible under pressure, or behave in ways that alter how forces are distributed within them. The structures of organisms reflect this. Hard shells and rigid frameworks become less common in the deepest parts of the ocean, not because they are impossible, but because they are less effective. Pressure acts uniformly, compressing from all directions, making flexibility a more stable strategy than resistance. Even the chemistry of water itself is influenced by these conditions. At high pressure, the interactions between molecules shift slightly, affecting how substances dissolve, how reactions occur, how compounds remain stable or break apart. These changes are subtle, but their effects accumulate, influencing biological systems in ways that are not immediately obvious. Enzymatic reactions, cellular processes, the transport of molecules across membranes, all operate within this altered context. What works at the surface does not always translate directly to these depths. This is why organisms in the trench are not simply scaled versions of their shallow water counterparts. They are fundamentally adjusted to the environment at a molecular level. Their proteins are structured to remain stable under pressure. Their membranes maintain fluidity where others would become rigid or collapse. Their internal chemistry is balanced to function within a narrow range of conditions that would disrupt most life forms. This is not adaptation in the sense of visible traits. It is adaptation at the level of physical interaction, where the distinction between biology and chemistry becomes less clear. One of the most challenging aspects of understanding this environment is that intuition becomes unreliable. The mental models built from surface experience do not apply cleanly. It is difficult to predict how a material will behave, how a reaction will proceed, how a structure will respond to stress. Even simple assumptions about density, buoyancy, flow must be reconsidered. The deeper the environment, the more those assumptions need to be adjusted. This does not mean that the trench is chaotic or unpredictable. It is governed by the same physical laws as any other part of the planet, but the parameters are different, and those differences produce outcomes that feel unfamiliar. It is not that physics stops working. It is that it operates in a regime that is rarely encountered, where the balance between forces shifts, where interactions that are negligible at the surface become significant. Yet this creates an environment that feels almost detached from everyday reality. Not because it is separate, but because it exists at the edge of what is commonly experienced. For organisms living there, this is not unusual. It is the only context they have ever known. Their biology is aligned with these conditions, their processes calibrated to function within them. For human observers, however, it requires a different way of thinking, a willingness to set aside assumptions, to accept that familiar concepts may not behave in familiar ways. The trench, in this sense, is not just a place where life adapts, it is a place where understanding must adapt as well. where the boundaries of intuition are tested and often exceeded. It reveals that the world is not defined by a single set of conditions, but by a range of possibilities, them each governed by the same underlying principles, but expressed differently depending on the environment. And in that variation, what seems impossible at one level becomes entirely consistent at another. What begins to emerge from all of this is not just a different kind of environment, but a different relationship with time itself. In the trench, processes do not stop, they slow down. Movement becomes less frequent, reactions take longer, cycles stretch outward in ways that are difficult to perceive without stepping back and looking across years or even decades. Life is still active, still functioning, but it is operating on a timescale that feels almost disconnected from the rhythms of the surface. At shallower depths, ecosystems are often defined by rapid change. Day and night cycles, seasonal shifts, migrations, growth and decay, occurring in patterns that are visible within relatively short periods. In the trench, those patterns dissolve. There is no sunlight to mark the passage of a day, no seasons to introduce variation. The environment is stable in temperature, stable in darkness, stable in its overall conditions. What changes does so slowly, influenced by processes that unfold over long durations rather than immediate fluctuations. This stability shapes how life organizes itself. Metabolism, the set of chemical reactions that sustain living organisms, is closely tied to the availability of energy. In an environment where energy is scarce, those reactions are reduced, slowed, adjusted to match what is available. Organisms in the trench often have lower metabolic rates than their counterparts in more active ecosystems. They consume less, move less, grow more slowly. This is not a limitation in the sense of deficiency. It is a calibration, an alignment with the conditions that define their existence. To operate at a faster pace would require more energy than the environment can provide, so life adjusts not by pushing against that constraint, but by working within it. This has profound effects on life cycles. Growth may take years rather than months. Reproduction may occur less frequently, with longer intervals between generations. Lifespans can extend not because the organisms are inherently more durable, but because their processes are stretched over time. The entire rhythm of life shifts, becoming less about rapid turnover and more about continuity. Persistence replaces acceleration as the dominant pattern. One of the clearest examples of this extended timescale can be seen in the sequence that follows a whale fall. When a whale's body reaches the sea floor, it initiates a process that unfolds in stages, at each one lasting far longer than a comparable event at the surface. The initial scavenging phase, where larger organisms consume the soft tissue, may last months, depending on the size of the carcass and the density of scavengers. But this is only the beginning. Once the easily accessible material is removed, the system transitions into a different phase, one dominated by smaller organisms and microbial activity. The surrounding sediment becomes enriched, supporting a community that develops gradually, sustained by the breakdown of remaining organic matter. This phase can persist for years as the nutrients continue to be processed and redistributed. Eventually, the carcass is reduced to bone, and even then the process continues. Lipids within the bones provide a long-term energy source, supporting specialized organisms that are adapted to exploit this resource. These communities can last for decades, forming a stable, localized ecosystem that persists long after the initial event. What begins as a single moment, the death of a whale, extends into a long-term transformation of the seafloor, a sequence that unfolds slowly, each stage transitioning into the next without clear boundaries. This extended timeline is not unique to whale falls. It reflects a broader pattern across the trench. Sediment accumulates gradually, layer by layer, recording the passage of time in a way that is almost geological. Organisms interact with this sediment, feeding, moving, altering its structure in subtle ways that become visible only over long periods. Even disturbances, when they occur, are absorbed slowly, their effects diminishing over time rather than being rapidly erased. This creates an environment where change is continuous but rarely abrupt. It is a form of activity that does not draw attention to itself, that does not produce dramatic shifts, but that is nonetheless constant. The trench is not static, it is moving, evolving, but at a pace that requires a different perspective to fully appreciate. For organisms living within this system, this pace is not unusual. It is the baseline. Their biology is tuned to it, their processes aligned with it. They do not experience time as slow. They experience it as normal. It is only when viewed from the outside, from a context where change is faster and more visible, that the difference becomes apparent. This difference challenges another assumption about life, that speed, activity, and rapid response are essential for survival. In many environments they are, but in the trench, where energy is limited and conditions are stable, speed offers little advantage. What matters is efficiency, the ability to maintain function over long periods with minimal input. This leads to a form of resilience that is not based on strength or adaptability in the moment, but on consistency over time. Organisms do not need to react quickly if the environment does not change quickly. They do not need to grow rapidly if resources are not abundant. Instead, they maintain a steady state, adjusting gradually as conditions shift, avoiding extremes that would require sudden responses. This creates a system that is less dynamic in the short term, but highly stable in the long term. It is not easily disrupted, not prone to rapid collapse. It persists, even under conditions that would challenge more active ecosystems, and in that persistence, it reveals another way in which life can exist. Not through constant motion or rapid change, but through a sustained balance, maintained over time scales that extend far beyond immediate observation. That sense of extended time, of processes unfolding slowly and quietly, does not end at the surface of the seafloor. It continues downward into layers that are even more difficult to observe, where the concept of an ecosystem begins to lose its familiar meaning. Because beneath the sediment of the trench, below the soft layer of particles that accumulate over time, there is another environment entirely. One that does not rely on visible organisms or movement, or even the kinds of interactions we typically associate with life. It exists within the rock itself, in spaces so small they are invisible without magnification, in conditions that seem even less compatible with life than the trench above. For a long time, this region was not considered part of the living world at all. It was seen as purely geological, a domain of minerals and pressure, of heat and chemistry, but not of biology. The assumption was reasonable. Without light, without a clear source of energy, without the structures that support ecosystems, there seemed to be no mechanism by which life could exist there. But as methods of observation improved, as samples were taken and analysed more carefully, something unexpected began to emerge. Within the rock, within tiny fractures and pores, there were signs of activity. Not movement in the usual sense, but chemical signatures, patterns that indicated the presence of microorganisms. Bacteria and other simple forms of life, existing not on the seafloor, but beneath it. These organisms do not form communities in the way surface life does. There are no food chains, no visible interactions, no clustering around shared resources. Instead, they're distributed throughout the subsurface environment, often isolated from one another, each occupying a small space where conditions allow for minimal metabolic activity. Their existence is not defined by interaction, but by persistence. They do not rely on organic material drifting down from above. In many cases, they exist in regions where such material never reaches. Instead, they draw energy from chemical reactions that occur within the rock itself. Some of these reactions involve the breakdown of minerals, where the structure of the rock releases small amounts of energy that can be captured and used. Others involve the interaction of water with certain elements, producing compounds that serve as a source of energy. In some cases, radiation from naturally occurring elements within the Earth contributes to these processes, breaking apart molecules in ways that create usable chemical gradients. These are not rich energy sources. They do not support rapid growth or complex structures, but they are consistent, and in an environment where time extends far beyond immediate perception, consistency is enough. The organisms that inhabit this subsurface environment operate at extremely low metabolic rates. Their processes are slow, sometimes so slow that they challenge the definition of life itself. They may divide only once over the course of years or even decades. Their activity is difficult to measure, not because it is absent, but because it is minimal, operating at the edge of detectability. And yet, they persist. This has led to the concept of what is sometimes called a shadow biosphere, not in the sense of being hidden intentionally, but in the sense of being largely invisible, existing alongside the more familiar forms of life without interacting with them directly. It is a biosphere defined not by abundance or diversity, but by distribution, extending through vast regions beneath the seafloor, occupying spaces that were once thought to be sterile. What makes this particularly significant is that it removes another layer of assumption about what life requires. Even in the trench, life on the seafloor is still part of an ecosystem. It interacts, however slowly, with other organisms, with the movement of nutrients, with the occasional influx of energy from above or below. But in the subsurface, those interactions are reduced or absent. Life exists without the need for a structured environment, without the need for a network of relationships that define an ecosystem. It exists on its own, sustained by local conditions operating independently. This suggests that life does not require complexity to persist. It does not need diversity, or visible interaction, or even movement in the conventional sense. It can exist in isolation, as long as the basic conditions for chemical processes are present. It can occupy spaces that are physically constrained, where resources are limited and interactions are rare. It can function at scales and speeds that are almost imperceptible. The implications of this extend beyond the trench itself. If life can exist within rock, beneath the sea floor, sustained by minimal energy sources and operating over extended timescales, then the range of environments that can support life is broader than previously understood. It is not limited to surfaces, to places where energy is abundant or where conditions are stable in familiar ways. It can extend into regions that are defined by pressure, darkness, and isolation, as long as the underlying chemistry allows for it. In this context, the trench is not the final boundary. It is a transition point between environments that are difficult to access but still recognizable, and environments that challenge the very definition of what it means to be alive. The surface of the seafloor, with its slow-moving organisms and limited interactions, is only part of the story. Beneath it, life continues in a form that is less visible, less active, but no less real. And as these layers are explored, as more is learned about the conditions that support life at these depths, the picture becomes more complex, not because the rules are being broken, but because they are being expanded. The limits of life are not fixed points. They are boundaries that shift as understanding improves, as new evidence emerges, as environments once thought to be empty are revealed to contain something more. What begins as a study of the deepest place on Earth gradually turns into something much larger, not because the trench changes, but because our understanding of life expands as a result of it. The patterns that emerge here, life without sunlight, ecosystems powered by chemistry, organisms adapted to pressure, time stretched across decades, begin to suggest that the conditions we once thought were essential are not as universal as they seemed. They are simply the conditions we're most familiar with. On the surface, habitability has always been defined by a narrow set of requirements: liquid water, a stable temperature range, access to sunlight, an atmosphere that can support chemical exchange. These criteria are based on Earth, on the environments where life is visible, active, and relatively easy to study. But the trench exists outside many of those assumptions. It has liquid water, but it lacks light. It has energy, but not from the sun. It supports life, but not in ways that align with surface ecosystems. And yet, it functions, not as an exception, but as a demonstration that the framework itself may be incomplete. This realization becomes more significant when placed in a broader context. Beyond Earth, there are environments that share some of these characteristics. Not identical, not exact parallels, but similar in the ways that matter. Beneath the icy surfaces of moons like Europa and Enceladus, there are oceans, vast bodies of liquid water kept from freezing not by sunlight, but by internal heat generated through gravitational interactions. These oceans are hidden, covered by thick layers of ice, isolated from direct observation. For a long time, they were considered unlikely places for life, precisely because they lack the conditions we associate with habitable environments. But the trench offers a different perspective. It shows that light is not required for ecosystems to exist. That chemical energy, derived from interactions within the planet itself, can sustain life in the absence of sunlight. It shows that pressure, even at extreme levels, does not necessarily prevent biological processes. That life can adapt not just to survive under those conditions, but to function within them. This does not mean that Europa or Enceladus necessarily contain life. It means that the possibility can no longer be dismissed based on the absence of surface-like conditions. The definition of what is habitable has expanded. It now includes environments that were once excluded, not because they were proven to be uninhabitable, but because they did not match a limited set of criteria. The trench becomes a reference point, not because it is identical to these extraterrestrial environments, but because it demonstrates that life can exist under conditions that were previously considered prohibitive. It shifts the question from where can life exist to what conditions can life adapt to, and that is a fundamentally different way of thinking. It removes the assumption that life must resemble what we see on the surface of Earth. It opens the possibility that life elsewhere may be structured differently, operate differently, exist in forms that are not immediately recognizable. This is not speculation for its own sake. It is grounded in observation. The organisms in the trench already challenge our expectations. They live without light, without abundant energy, under pressure that alters their chemistry. They exist in environments that would be considered uninhabitable by traditional standards, and yet they are not anomalies. They are part of a system that is consistent, stable, and persistent. This suggests that life is not defined by a specific set of conditions, but by its ability to adapt to the conditions that are present. The environment shapes the form, not the other way around. And if that is the case, then the range of possible life-bearing environments is much broader than previously thought. Earth, in this context, becomes more than just a single example. It becomes a model, a collection of environments that demonstrate the range of conditions under which life can exist. From the surface to the deepest trench, from sunlit ecosystems to chemical ones, from rapid cycles to extended timescales, it shows that life is not confined to a narrow band of possibilities. It is flexible, adaptable, capable of existing in ways that do not align with initial expectations. This has implications not only for the search for life beyond Earth, but for how life is understood in general. It suggests that the limits we identify are often reflections of our own perspective, shaped by the environments we're most familiar with. As exploration extends into less familiar regions, those limits begin to shift. Not because the rules of science change, but because our interpretation of those rules becomes more complete. The trench does not break the rules. It reveals their full range. It shows that the same principles apply across a spectrum of conditions, producing outcomes that vary depending on the environment. What appears impossible under one set of conditions becomes entirely consistent under another. And this consistency, across such different contexts, is what allows the concept of life to extend beyond a single planet. The more that is learned about environments like the Mariana Trench, the more it becomes clear that life is not an isolated phenomenon tied to specific surface conditions. It is a process, one that can occur wherever the necessary chemical interactions are possible, regardless of whether those conditions resemble what we experience. The trench does not provide direct evidence of life elsewhere, but it changes the way that evidence is interpreted. It broadens the search, redefines the criteria, and suggests that the question is not whether life exists under extreme conditions, but how many different forms those conditions can support. By the time the descent reaches its deepest point, what once seemed like a boundary begins to feel more like a transition. The Mariana Trench is not the end of something, not the place where life stops or where the planet becomes empty. It is where assumptions begin to fall away, one after another, until what remains is not a lack of life, but a different expression of it. Everything that was expected to define the limits of existence, light, warmth, abundance, even stability, has been removed or altered. And yet, the absence of those conditions does not result in silence or emptiness. It reveals something quieter, more deliberate, but no less real. The deeper the exploration goes, the more it becomes clear that the trench is not defined by what it lacks, but by how life adapts to those absences. It is easy to imagine the deep ocean as a void, a place where nothing happens because nothing can. That image persists because it aligns with surface intuition. Darkness suggests emptiness. Pressure suggests hostility. Distance suggests isolation, but each of those impressions is incomplete. Darkness does not prevent interaction. It changes how interaction occurs. Pressure does not eliminate structure, it reshapes it. Isolation does not mean separation. It means connection through slower, less visible processes. The trench is not empty. It is simply difficult to perceive. What has emerged from this understanding is not just a catalogue of unusual organisms or extreme conditions, but a shift in perspective. Life is not limited to environments that resemble the surface. It does not require familiarity. It does not depend on visibility or speed or even abundance. It operates across a range of conditions, some of which are so different from everyday experience that they seem incompatible at first. But compatibility is not determined by appearance. It is determined by whether the underlying processes can function, and in the trench, they do. This does not mean that the environment is easy, or forgiving, or rich in the ways that surface ecosystems are. It remains one of the most extreme places on Earth. But extremity does not equal absence. It creates constraints, and within those constraints, life adjusts. Not by overcoming them in a dramatic sense, but by aligning with them, by becoming part of the system rather than resisting it. This is what makes the trench so difficult to fully understand. It does not present itself in obvious ways. It does not offer clear, immediate evidence of its complexity. It requires patience, careful observation, a willingness to accept that what is not immediately visible may still be present. And even then, the picture remains incomplete. There are still regions that have not been explored in detail, still processes that are not fully understood, still organisms that have not been observed directly. The trench is not a solved problem. It is an ongoing area of discovery, one that continues to challenge the boundaries of what is known. This reflects something broader about the planet itself. Earth is often described as well understood, mapped, categorized, studied across disciplines, and in many ways it is. But that understanding is uneven. It is concentrated in places that are accessible, where observation is straightforward, where conditions align with the tools and methods available. In environments like the Mariana Trench, that understanding becomes less complete. Not because the environment is fundamentally unknowable, but because it requires different approaches, different assumptions, a different way of interpreting what is observed. The limits of human understanding are not fixed. They expand as methods improve, as technology advances, as exploration reaches further into regions that were previously inaccessible. But each expansion reveals not just new information, but new questions. The trench does not provide final answers. It introduces complexities that were not part of the original framework. It shows that the world is more varied than it appears from a single perspective, that what is considered normal is often just what is most familiar, and that familiarity can obscure the full range of what is possible. In that sense, the Mariana Trench is not just a place, it is a reference point, a reminder that there are environments on this planet that do not conform to surface expectations, that operate under different conditions, and that support life in ways that are not immediately intuitive. It challenges the idea that knowledge is complete, that the boundaries of understanding are clearly defined. Instead, it suggests that those boundaries are flexible, shaped by what has been observed and what remains to be discovered. The story of the trench is not one of isolation, or extremity, or even depth. It is a story about perception, about how assumptions are formed, how they are tested, and how they change when new information becomes available. And it is about recognizing that absence of evidence is not evidence of absence, especially in environments where observation is limited. And it is about understanding that the world is not constrained by the conditions we're most familiar with. The deepest place on Earth was never empty. It only appeared that way because we did not yet have the means or the perspective to see what was there.